Okay, good morning everybody. Let's dive in. We got a fair bit of housekeeping stuff to talk about before we get back to lecture. Let's talk about the rest of this week and next week. You are working on deliverable 10, which is due next Monday. After deliverable 10, you're going to be starting in on 3 weekly interim videos, and these videos are going to be snapshots for us to observe your progress towards your final project. So we'll talk about the interim video and the final project a little bit today, and we'll come back to that later. Next week, I'm going to be at a conference in China. This is my last trip for the season, so you will have 2 guest speakers next week. Josh Powers will be back on Tuesday to walk you through human-robot interaction. On Thursday, another one of my graduate students will be here, Sam Kriegman, and he's going to talk about visualization in scientific communication. So he's going to walk you through some of his research and some of the visualizations he's created to try and communicate his research. So you will be in the more than capable hands of Josh Powers and Sam Kriegman next week. I'm sorry? Can Sam bring his dog? You'll have to, if you know Sam, you can ask him. It's up to him. Okay, good question. Let's see. So let's talk about the final project. Usually I would talk about this next Tuesday when you've finished and submitted deliverable 10. I won't be here next Tuesday, so we're going to talk a little bit about it now. So if you click on the interim video link, it will take you to a new document which contains all the information you need to know about the interim videos and the final project. So if you have any questions about that, click on that link. Everything should be in here. Obviously, you'll notice some stuff is in red that I will fill in as we go. First thing, please remember, during our exam period, you're going to be presenting your final project orally in class, and when you finish, you will hand back your Leap Motion device to us. So there will be a Leap Motion device for a student next year. Please, please, please remember to bring the Leap Motion device to the exam period on Tuesday, December the 10th. Okay, so again, I'm not going to talk too much about what's going to happen on the 10th, but just to give you a heads up, you're going to be working on your project, your final project, up to the exam period. The night before the exam period, you will be submitting a very short video. It will probably be about 3 minutes. We have about 60 people in the class. We have 3 hours. If you do the math on that, it's about 3 minutes per person. 3 minutes is not a lot of time. You're going to be shooting a silent 3-minute or so video. In the exam period, I'm going to write up the order of presentations. When your video comes up in a YouTube playlist, you will stand up and come to the front, talk over your video, sit back down. The next 3-minute video on the playlist will come up. You will come up, talk over your video. We press play on the YouTube playlist at 7:30 in the morning on Monday, December the 10th. Sorry about 7:30, not up to me. Press play on the YouTube video. We will have 60 3-minute videos running, which will get us through everyone's presentation in a little less than 3 hours. Sound good? Takes a little bit of planning to make all this run smoothly, but we'll talk about the logistics a little bit later. Okay. The most important thing is to remember that you're going to have to submit your video the night before. If you submit the video that morning, obviously we can't put it into the playlist. It's too late. You don't present, no grade for the oral part of the final presentation. So just keep that in mind. Okay. So what are you going to be doing? Between now and the submission deadline, you're going to be adding in some new functionality to your system, right? We've already talked about this quite a bit by now. Most of you have a functioning system that is okay at teaching somebody ASL. You're going to be adding some new functionality and demonstrating that throughout between now and the submission period about how you've added in some functionality that helps users learn ASL. It's going to be up to you in the interim video to demonstrate to us what the new functionality is that you're adding. And the remaining videos are going to show that users are better at learning ASL using that new functionality. Okay. So it's up to you what you want to add. That's the difference between the interim videos and everything you've been doing up till now. You've got a lot more freedom. Here are some examples of things that students have done in the past. And I give them to you just to sort of get your brain thinking about things you might want to add, and also to give you an idea about sort of the level of complexity we're looking for in that added functionality. So, for example, you might add in some letters in addition to digits. Obviously, that would require you to retrain your KNN algorithm. You'll obviously, if you add letters, be training your KNN algorithm only on your hands, which might make it more difficult for your KNN to recognize letters being signed by another user. But again, we'll leave that up to you. Okay. You could, for example, add in the letter J, which requires motion. So at the moment, you've been taking a static snapshot. You've been capturing a single frame from Leap Motion device and pushing that all the way through your pipeline until KNN makes a prediction on the far side. You could alter your KNN algorithm so that instead of taking a single frame of data, it's capturing a few frames of data over time as somebody is signing the letter J. Requires a fair bit of change to the early stages of this pipeline, but KNN doesn't care, right? At the end, it's just expecting a set of features. You could decide that in order to keep your user engaged, maybe you add in a little bit of complexity and you add an additional scaffold while at the same time that your user is learning ASL, they're also starting to learn some basic math. So you flash up the digit 3, they have to sign the digit 3. If they get that right, you flash up 3 plus 4 and they have to sign 7. If they do a few of those correct, then you move on to variables and so on, right? You could add an additional learning gradient, which maybe mixes things up a little bit and makes things a little bit more interesting for your user. Okay. Perhaps you gamify your system in some way to, again, incentivize the users to stick with it. Again, these are just examples and give you a rough estimate of sort of the amount of new functionality we're looking for. Any questions at this point before we move on? Yep.
Like turns, like can we go 2-player?
That would be a great idea. Turn it into a 2-player game. Absolutely, that would be a perfect example.
We only need to present our video. Do not need to present our program.
You are never going to present your program to us. We are never going to see your code. You're demonstrating everything through video. Yep, exactly. Okay. Okay, so let's talk about these videos. You're going to be submitting 3 of them Monday night for the next 3 weeks, skipping over the Thanksgiving break. Okay. The first interim video will replace your worst deliverable. So if your worst deliverable is 2 out of 5, you get 4 out of 5 on the interim video. We'll replace your worst video with 4 out of 5. For the lucky few of you that have perfect on all your deliverables, we'll talk about it. Okay, so in this first interim video, you are going to submit a video as always, but talk over it. So you're going to narrate for Caitlin, the TA, and you're going to tell us what your new functionality is at the same time as the video is demonstrating that new functionality to us. Okay. So in this case, we just want to be able to see the beginnings of that new functionality, right? So for example, if you're doing math, we see individual digits, and if the user signs 3 or 10 digits correctly in a row, then we start to see pairs of digits showing up. Okay, I think that should be pretty straightforward. That's due not next Monday night, which is your deliverable 10, the following Monday night. Okay. What about the one after that? Interim video 2 is worth 2% of your final grade. You'll be shooting another short video. But in this case, we're going to be seeing not you demonstrate it using your system, but another user. So hopefully there is someone in your social circle that you have not shown your Leap Motion system to. This is going to be your naive user. And the idea is put them in front of the Leap Motion device. Do not tell them what it is. You can start them off perhaps by telling them to put their hand over the device. If you want, start the video, and we should see the user not necessarily interact perfectly with your system, Maybe they do, but we might see things like them being a little bit confused. Perhaps they get their hand over the device and your program is in state 1, and they look at you and they take their hand back out of Leap Motion's field of view and it goes back to program state 0. They look at you, you don't give them any feedback, they look back at the device, they put their hand back over the device, that's fine. What we would like to see in the video is your screen and the user's hand. We don't necessarily need to see their face or where they're looking. I think the hand should be enough. Okay. Okay, so again, we and you are looking to see from this naive user where the weak spots in your system are at this point in time, right? So what we're looking for is that you can communicate that to us clearly. This part seems to be intuitive to the user and they knew right away what to do, or at this point they paused for quite a while and it took 5 or 6 or 7 or 10 seconds until they did whatever they were supposed to do, right? So related to that, at the end of this video, you're going to flash up a spreadsheet, and this spreadsheet is just a sketch of some quantitative data. So while your user is interacting with the device, you might want to have a clipboard and a stopwatch nearby where you're timing some of these things. How long does it take the user to switch from state 0 to state 1? How long does it take them to switch from state 1 to state 2, right? You might very quickly write down how many seconds as they go.
When you say spreadsheet, should we be like doing that same test with a significant number of people?
Just one person, the naive user. So later on, you're going to be testing with 2 or more people. For now, it's just one person. So you take your naive user, you sit them down in front of your device, you take out your clipboard and your stopwatch, and you start them off by asking them to put their hand over the device, and you start writing down timing information. Afterwards, you type it into your spreadsheet and add that to the video. Make sense? It doesn't matter to us too much what you're putting into the spreadsheet. We don't expect a huge amount of data, but as I said, this is meant to just be a sketch, right? You're starting to capture some quantitative data. How long does it take them to switch from one state to another? How often do they go, quote unquote, backwards? Do they go from state 2 to state 1? They're confused or distracted or something goes wrong and they intentionally or unintentionally back up in your system and try again. Okay. Just as a reminder, for the undergraduates in this class, you're not going to be doing too much more user testing beyond this. You're going to be doing this again with a few more users over the Thanksgiving break. But for the graduate students, you're going to be doing this with many more than 2 people, and we'll talk about that when I'm back from China in 2 weeks' time. Okay, interim video 3, we're kind of getting ahead of ourselves here, but might as well just talk about this. You're submitting a 3rd video where you show another increment of your added functionality. So you're sort of almost finished at this point with your total functionality. For example, if they sign 10 digits in a row correctly under 3 seconds, the system switches to math and goes further into math as they do well, and it backs up to simpler math and back to individual digits if they're getting confused and performing poorly. So we might start to see the adaptive scaffolding in this 3rd video. Okay, I think I will talk about the written report and the oral presentation later. You can go and read this document at your leisure. Any questions about interim videos? Yes?
So there's no way to do sound on video?
If sound is integral to your project, that's okay, as long as it's not, as long as you can talk over it. So if there's voice, obviously that's going to be a problem. If you have music or sound or whatever, that's fine. Good point. It doesn't necessarily need to be silent, as long as you can speak over the video as you present it. Any other questions? No? Okay. Okay, so we are continuing on with our theme on looking outward, and we are partway through this final part on a particular class of technologies, which are embedded devices, which sense the world in real time. But our robots are a particular class of embedded devices which are active and not passive. They're not riding along with us as wearables and passively collecting data. Robots can, in some form, push against the world. They can act against the world and observe how the world pushes back. And we ended last time by looking at a few very simple robots, the Bratenberg vehicles, which among other things might make you a little bit nervous about how special you are compared to Bratenberg vehicles. But we will leave that philosophical discussion where we left it last time and continue on with our Bratenberg vehicles. The important thing from an HCI perspective is to notice here that the internal complexity of the machines is very, very low. 2 sensors, 2 motors, and 2 wires. But if we think carefully about what we want the robot to do, like chase a light or avoid the light, if we think about the interaction carefully, what happens when the robot moves? What's the sensory repercussion at the next time step? If we think about that interaction carefully from an HCI point of view, we can get away with a much simpler robot. If we don't think carefully about the richness of the potential interactions between this machine and its world, we might end up building more and more complexity into the device. For example, if we want 2B, the aggressor, to chase the light, we might decide to put a camera on the robot and do some image processing, find the light source in its field of view, triangulate the position of the flashlight in its field of view, and turn in that direction and move towards it. We don't need that. All we need are 2 light sensors connected appropriately to the 2 motors. Okay. We talked about IPSA and contralateral connections last time. Let's look at vehicle 3A, which has IPSA lateral connections, same side connections. But the connections now are no longer excitatory, they are inhibitory, indicated by the little minus sign. So excitatory is a term stolen from neuroscience. So an excitatory synapse, if a neuron fires, it tends to trigger the firing of the neuron that it connects to. An inhibitory connection between 2 neurons. An inhibitory connection means that the more the source neuron is firing, the more it inhibits the firing of the target neuron. So in our case, when we add an inhibitory connection to a Bratenberg vehicle, the more the light sensor fires, or the stronger the signal at the sensor, the more it slows the turning of the wheel that it's connected to. Make sense? Okay, so here's 3A, ipsilaterally inhibitory connections. Let's imagine that we forget the dotted line here. Let's say we add a light source here, front right of the robot. What is the robot going to do if it senses more light on its right than on its left?
It's going to kind of chase it and be very standoff with it. It's going to make sure it's always looking at it, and then if it's straight on with it, it's going to play possum and not move.
Very good. So you're using Bratenberg type language here, right? If there's the light source is on the right, then there is more inhibition of the right motor than there is of the left motor, which means the right motor, the right wheel will spin slower and it will turn towards the light. But at the next time step, when it's facing the light, it's closer to the light, which means there's more inhibition and it will slow down and play possum, or instead gaze with quiet admiration at the light source which it loves, right? It will chase after a light source, and when it gets close and it faces it, it will slow down and stop in front of the light source.
If there's no light source at all, it just continues to move. What does it need light?
Exactly. So given this cartoon, and again, obviously it's a cartoon, there's not a lot of detail here. If you were to place vehicle 3A in a perfectly dark room, no light at all, what does it do? It just goes really fast straight, right? You smash into a wall, it's upset because its lover isn't around, right? Loves light. Okay. 3B, same thing, inhibitory connections, but now contralateral connections. How does vehicle 3B behave in the presence of a light? It's going to turn away, right? So let's put the light source here. Light source is front right of the robot, which means there's more light on the right, which means there's more inhibition of the left wheel. So it's going to turn away from the light. The moment that it turns away from the light, there is less light landing on the wheel, on the sensors, which mean it's going to do what at the next time step? It's going to accelerate away from the light. So again, depending on how you do this, you can think of this as the explorer. It's moving around in its environment. If it gets near a light, it'll slow down for a while because it's nearer the light, which means there's more general inhibition, but it'll slowly turn away and head off in a more or less straight direction until it gets near another light source, slow down near it, turn away, and continue on. Okay, so again, the point here is to see that with very simple machines and making slight changes to them, we can alter the kind of behavior or the interaction we get between the machine and the environment. Okay, vehicle 3C. It's the last one, okay. 8 sensors. We have 4 pairs of sensors. So we have a pair of light sensors, front left, front right, a pair of temperature sensors, a pair of oxygen sensors, a pair of organic material sensors. The first pair has crossed excitatory, the second uncrossed excitatory, and so on. How does this vehicle behave in an environment that has light sources, temperature gradients, more or less oxygen in certain areas, and organic material in different directions? We have rotting fruit somewhere in the environment, and it's giving off organic material that's diffusing away from the fruit.
What's its objective? It will just go towards whichever one of these it senses a stronger signal.
So the question is, what is its objective? It has no objective. There's no objective inside. There's simply 8 sensors, two wheels, and 8 wires.
But I guess my question is, if one sensation or is stronger than the other, is it just going to move towards that thing? Or?
Good question. So if one signal is stronger than the other, right? There's a light source far away, but it's right in front of a piece of rotting fruit. Which one wins? This cartoon doesn't really tell you. You'll notice that there should be 1, 2, 3, 4 incoming connections to each wheel, some excitatory and inhibitory. So what's going on at the wheel? At the wheel, we are summing all of the incoming values, taking the average, and that average becomes the wheel's speed. It could be the fruit fly, so maybe it goes towards fruit and away. It goes towards rotting fruit, but what if there's a light source right next to the fruit?
So yeah, so it's going to go towards the light, away from heat, and then I think away from oxygen and towards organic material.
Exactly. So we can, as you were just doing, we could itemize its behavior in the presence of one and only one of these 4 stimuli. That's easy. But pairs of stimuli is difficult, right? It's near rotting fruit and a light source. Tricky. That's the point of vehicle 3C. Even in a relatively simple machine like vehicle 3C, it is very difficult for a human engineer to sit down and infer, given this wiring diagram, what behavior is going to result. And again, this is a perspective issue, right? It's very difficult to think about what a particular wiring diagram might do. So not surprisingly, in robotics, we use an AI method or machine learning to try and discover what particular wiring diagram we want for a given behavior. The robot should do this and should not do that, and in combination of these stimuli, it should do something else, and so on. Very tricky. Okay. Okay. So again, this idea of perspective is very important especially when we're dealing with machines that are active rather than passive. They are able to act on the world and get some sensory repercussion, which builds these action-reaction feedback loops. Very difficult to design a wiring diagram for some desired behavior. Or if we invert the problem and say we have the the wiring diagram, what behavior results. Very difficult for a human to figure this out. So from a perspective point of view, if we were to hide these wires and you were just to watch the organism or the vehicle or the machine behaving, you might come up with a complex mental model. The robot is judging which is closer, the light source or the rotting fruit, compares those two values and decides to go after the fruit or away from the light. We might incorrectly infer more complexity than is actually there if we observe the device. If we open it up, however, obviously we're kind of cheating because we know what's inside, and it's often simpler than we think. The complexity is not necessarily in the wiring diagram, it's in the feedback loop that results from the wiring diagram. Okay, so if we want to design machines that are active and work safely and competently alongside us in the real world, instead of trying to create an overly complex machine, as we all know, the more complex a machine is, the more ways it can go wrong. Can we as HCI designers help here by thinking carefully about the environment in which the machine is going to operate, and instead come up with a simpler machine that exploits this feedback loop? It uses that as an opportunity rather than a challenge. So, as I just said, we're going to try and think about this from different perspectives. The implications for us from this first lesson is, again, we want to try and build as simple a machine as possible, but a machine that exploits the richness of its environment. And as always in HCI, we want user testing to be front and center. In this case, it's robot testing. What happens if this wiring diagram is placed in the machine and it's let go in its natural environment? What can I learn from that? Okay. So I'll give you a few minutes now to try and design with pen and paper your own Bratenberg vehicle. You're going to do this with a neighbor, and you're going to be creating a swarm of robots. And these robots are going to collectively build a base on Mars. Should be easy, straightforward. We're going to assume that our robots have 3 pairs of sensors. They have 2 light sensors on their front left, front right. They have a pair of heat sensors, front left and front right, and a pair of sound sensors, front left and front right. Finally, our robots have a gripper on the front, and there is a touch sensor inside the inside surface of the gripper, so the robot knows that it's grasping something or it's not. Okay, so those are the sensors that you have available. We are going to scaffold the Mars base to make it easier for the swarm to construct the base. How are we going to do this? We're going to send some supplies to Mars before the robots ever get there, and we're going to drop those supplies onto the surface. We're going to drop a whole bunch of objects, which are the HABs, and we're going to assume that there are light sources on top of them, so there's a beacon on top of them. We're going to drop one other object, which is a heat source, and the heat is in essence saying this is where the base should be constructed. The robots should obviously avoid one another, but they should find all these objects, grab them, and bring them to this central location. That's the idea. No individual Bratenberg vehicle is going to do this. Obviously, a 2A vehicle, which responds only to heat, is not going to be able to find the objects with light, and a 3C vehicle that only responds to light is not going to be able to find the heat source. So what you're going to do is to sketch an if-then statement like the one here. This might be a good first sketch. If the gripper touch sensors are firing, so if the robot is holding an object, it triggers a particular internal vehicle. So you can think of the Bratenberg vehicles now as virtual machines. It has a library of Bratenberg vehicles that it can choose from, and the particular vehicle that it acts like is dependent on its current situation. So if the robot is holding an object, then if there's heat on the left, spin the right wheel. If there is heat on the right, spin the left wheel. What does that result in? The robot is holding an object. If it runs this vehicle, what happens?
towards the heat source.
It moves towards the heat source, which is part of the solution here, right? If it's not holding the light source, so you can add an else statement here, else it's going to run a different Bratenberg vehicle, which should further help with the mission. You might then take those if then else statements and replace one of these with another embedded if statement, because possibly there's other things it needs to do. So turn to your neighbor and start on a piece of paper by writing this with lots of vertical spacing between the if then and else. So you can then go back on a second pass and add in some more complexity to your if then else statement. And let's see how well you can do at creating a swarm for Mars. Is there sound on Mars? Mars has a very thin atmosphere, so sound doesn't travel very far, which is a bit of a hint. Okay. You can make any other assumptions about Mars you want. That's fine.
First, we need to find the light one. Yeah. Then go to the green one. Stop. Release.
So to search for the
Yeah, and then
say
and
if it's not
then
green,
it's
something.
opposite that. Right, so you try to avoid the robot stand.
It should have inhibitory uncross, so that way it turns.
Right, but if they're both
It
running,
goes into
one
the-
avoid the robot stand,
My worry with the excitatory is because that should, I don't know, because I feel like it should, what if it can't see any light? It'll just stop. So I feel like it should be half Yeah, then it'll turn, and then it'll go forward.
Sorry, it's contralateral, and then what's the other one where it doesn't cross?
Contralateral is across.
And then
Ipsilateral is the same side.
it will be this one.
Yeah.
So there's
Oh, that's a good idea.
They're spread out.
Yeah, so yeah, so there's one here, here,
Yeah,
here.
and
If
then
it
like
moves
there's
here,
one.
takes it up, it's gonna then have a light source.
Yeah. And then,
Then it goes
I think that we read that saying that they should avoid each other, and so I think that we should also use some of that. But we can use it in this way too.
yeah.
So maybe if it's because if it's going towards the light, it'll be accelerating, right? So how about if it's accelerating and it lets us out and then
How does it tell if it's close enough?
I think it's
Maybe the light
things
to
working
like.
all the time.
Yeah. So there's a question about how does the robot know that it's close enough to the heat source or close enough to the light source? You can make whatever assumptions you want. If total light is above 0.8, then we will assume that the robot can sum the total amount of stimuli, and that can become a conditional if you want.
then stop the light. Same thing.
That's not a problem, right? Because it's always moving away from the sound.
I was talking about like dropping things to someone.
Yeah.
So maybe if it crosses over a certain amount, it stops completely, drops it, and then waits a moment to
Avoid each other. I think that if it's how do you do that? How to explore.
I guess you could be like, okay, so what's happening? The exploring machine was
have it going inhibitory contrary.
As if it would be like an area.
Yeah, but I think that means that it should just turn as much as it has together.
I think it's like a mini.
So you could do here, instead of check out. So if you say, okay, this is home now.
Yes.
Okay, let's see what you came up with. Let's add a little bit of detail to this scenario here. Let's imagine that you've been hired by NASA and you are working in a very large team where you are actually trying to prototype some of these ideas. This team is made up of a number of engineers, roboticists, life scientists, clinicians, biologists, geologists. You are the one HCI member of the team. So obviously the idea is that people are contributing to this very hard problem from very different perspectives. What are some aspects of this task that hopefully are obvious to an HCI designer but maybe less obvious to a roboticist or the civil engineers that are involved in putting together this habitat? Ideas?
Well, one thing that occurred to me was that they need to be able to turn off the lights
Okay.
on the objects.
How come?
Because if you just started collecting all the objects with lights on them, then you would never be able to find them.
So if we have a Bratenberg vehicle in here that when the gripper is empty, go towards the light, which would make sense, you're going to have some problems, especially once objects start to accumulate near the light source, near the heat source. It's going to have a lot of lights, right? So physical context, which is tied to the task itself. At the beginning, maybe we assume the light sources are distributed more or less uniformly across a very big surface area. But as the task progresses, there's going to be a greater and greater concentration of one of the stimuli to which the robots are responsive to. So we may propose to the engineers a change that the lights are turned off at some point. Or alternatively, we add some complexity to our robot controller here, which is if there's a lot of light but also a lot of heat, then ignore the light. There's different options here, but again, that's a good observation about context, which matters.
It's very similar. What if another robot's carrying the light source?
What if another robot's carrying the light source? Absolutely, right? You're going to get robots fighting over the same object. What about sound? Why does this matter?
Originally, now that I'm thinking about it, it was used to determine whether or not it's close to another robot so that to avoid collision. But if you're using the sound to determine whether or not there's another robot, what if it hears itself and doesn't know where to go?
Exactly, right? So the sound hopefully was a hint to you that assuming a very small atmosphere, a very light atmosphere, the only sound presumably is going to be the sound of other robots and self. Remember the example about social network inference with the grad students that were wearing a microphone? The microphone was recording their speech as well as others. So possibly we add in some thresholding where if the volume is not too high, which is probably going to be true most of the time because I hear myself, but if I hear an intermediate sound, that means there's another robot nearby, for example, right? Or maybe I subtract out my own volume. What are some other elements of this task? What are some other aspects of context here that influenced your construction of these conditionals?
The inability to set up a waypoint or a distribution center for where you're going to put all the light sources after you grab them.
Okay, so assuming that a waypoint may be useful, why? Why might that be useful?
Because then you could get yourself to a light source, grab the new ones, but now where you're gonna put them? You could eventually start moving everything closer together, but then, did I already move this one? How's it gonna go to track?
Did I already move this one? Yeah, maybe that's important.
You would need the robots to interact with the objects, right? Because like as soon as you pick it up, you need to turn the light off so that you don't have a whole bunch of robots fighting over each other, and that also kind of indicates, oh, this one's already been moved.
Absolutely. So the robot grabs the object, and that either triggers turning off the light on the object itself. We haven't said anything about the robots themselves. Maybe the robots are designed so that they're big enough that when they approach and grab an object, their body shrouds the light from other objects, right? They grasp like this and cover the light rather than like this. We could start to talk about the design of the robots themselves to again simplify the programming required for these machines.
Is the light just a regular kind of white light, or can it be, RGB light?
Good question, right? So we're in the early planning stages, so maybe we confer with the engineers that it would be extremely useful to make more robust behavior and to be able to add some more behavior if we increase the interaction, right? There's red, green, we increase the opportunity for different kinds of interaction. So put the complexity out in the world, replace the white light with red light, green lights, and blue lights, which allows us to simplify the internal programming of the machine, which keeps the machines themselves simpler, which is always a good engineering approach.
I mean, if we were really considering putting this on Mars, you'd also have to consider like, how does the dust on Mars impact the performance of using lights to navigate?
Absolutely, right? So we've got a lot of astronomers and planetary scientists there as well. Most of us know, yeah, dust is probably important. There's probably a dozen other subtle phenomenon that would be on the Martian surface that, as an HCI designer, you may not know about, that we would try and elicit from the other members of the team. What else besides dust may influence our design choices here? Hopefully you as the HCI designer would know who to ask and what kinds of questions to ask to elicit the subtle context that might be at play in this scenario, rather than ignoring it and trying to create a complex machine from scratch. Question?
So, well, I was just going to mention like the temperature on Mars, so we need to consider if the heat source is going to be enough to differentiate, or too much or too little, etc.
Exactly, right? So all three of these phenomena, heat, light, and sound, we're assuming that they're diffusing outward. But how? I don't know much about Martian atmospheric science to be able to answer that question. But I might know as an HCI designer to ask those kinds of questions.
Also, the location on Mars is like Valles Marineris, if it's in a trench versus the polar caps, which are ice.
Absolutely, right? All of these things may matter. Okay. All right, again, just an example to show that we want to think very carefully about context before we start talking about the interactive technology itself. Okay, so let's move on now to situated and embodied cognition. So we're going to look at cognition now from the point of view of the robot, not from the human. This idea of situated and embodied cognition, these are just adjectives to talk about different ways of thinking, different kinds of cognition. People are literally situated in the world. We are here and receiving sensory information in real time, and we are embodied in the sense that we have a body and we can push against the world. Sometimes that interaction is a social interaction between different people. Sometimes it's directly with the environment. Sometimes it's with both. But in this course, we're thinking mostly about interactions between people and the technology. Again, what if the technology pushes back? So I've used this phrase, push against, and observe how the world pushes back several times. What really does this mean? The moment that the robot or an organism moves itself, most of its sensory signals change, right? It's very different from being stationary and moving an arm or moving something else, or like a non-embodied machine waiting for something to happen from the outside. So not only do robots cause sensory repercussions, but they cause immediate sensory repercussions. The moment I move, a lot of other things in my sensorium change. Of course, traditional computers like laptops and desktops, they have a physical casing It's not a body. They can't exploit it. They can't move it or influence the relationship between that box and the environment. The little Lego robot over here, it can. If it's sensing the distance between itself and this object, when it moves, that distance instantaneously changes. That's unavoidable. What the machine chooses to do with that immediate feedback, that's up to the designer, right? Or up to the robot. Okay. So let's talk about situated cognition first. So this is the idea of embedded devices, this real-time sensory feedback. The way you process information is affected by the fact that you are right here in the real world. A non-situated machine, like a laptop, is passively sitting and waiting for packets to arrive. These changes in an embedded device in situated cognition occur in real time. They're not really under the control of the device. So in another way, it's kind of passive. Stuff is coming in. It can't slow the rate of incoming information unless it's capturing it and putting it in a buffer. But one of the biggest challenges for machines and organisms that operate in the real world is usually our buffers are insufficient. There is a huge amount of information coming in at any one time step. Not only is there a lot of information, but there's a lot of information that is changing as I'm going about trying to do whatever I'm doing in the real world. Okay. So a wireless sensor, like an intelligent light sensor in the Davis Center, it's not a robot, can't move itself. But it is sensing changes in light level, and it doesn't have any control over that. Light in the room is changing regardless of what the machine itself does. Okay. If we're going to talk now about complete agents, so an agent is like vehicles, it's just going to be a placeholder word for human, animal, robot. A complete agent is both embodied, it has a body and can push against the world, and it's situated. It is receiving sensory feedback in real time. In the reading for today, you'll see that complete agents have at least 5 properties that are interesting from a robotics point of view, but only 3 of these are really interesting for us as HCI designers. The first one, which is if you have a body, you have a physical body, it's in the physical world, it's subject to the laws of physics, right? It's got mass, nothing we can do about that. They generate sensory stimulation instantaneously the moment they move. There's nothing we can do about that. You can decide what to do with that immediate sensory repercussion, but it is going to happen. It's unavoidable. And the environment itself is malleable. The moment I act in the world, I also have a physical impact on my environment as well. I can try and minimize my impact, but I'm going to have some impact in some way. Why is this important for HCI? Well, often these are viewed in robotics and also in HCI as sort of challenges, things that have to be minimized or gotten over. But in HCI, we're always trying to think about exploiting real-time interaction, in this case between the machine and its environment. So instead of thinking about these 3 unavoidable phenomena as challenges or roadblocks to creating useful technology, we want to think about technology that can exploit these phenomena. So let's start with the first one, which is kind of the easiest one. So let's go back out into the solar system. We know that embodied devices are subject to the laws of physics. We'd like to design a device that can record information from different levels in the atmosphere of Saturn's moon Titan. So here's a few snapshots, which of course we've already done. We could, for example, create a satellite that orbits Titan, and we create very sophisticated radar and infrared and ultrasound where we can send out signals into the environment. And by tuning those wavelengths very carefully, we can control at what level of the atmosphere that signal bounces back. And then when we receive that signal, we can infer something about Titan at that level in its atmosphere all the way down to the level of the ground. Not a great solution, right? We have a device that is distant and is trying to do some very complicated indirect measurements of the environment. So the obvious alternate solution is land it, right? So as the probe is coming through the atmosphere, it's taking measurements as it goes, and we just let Titan's gravity do what Titan's gravity does. If we're going to something like a small moon, the gravity is less, and we can assume the thing won't smash on impact. We might try and slow the device in some way so that we can capture actual information at ground level. This is obviously what actually happened back in 2005 with the WHAT probe. Anybody remember? There's a recent one. This was back in 2005. So this was the Huygens probe, which was sort of the first time to actually try and do this on an external planetary body, was to take very detailed readings at different levels of the atmosphere while the object itself is falling. Okay, let's look at number 2 and 3 now. Robots can generate sensory stimulation through their behavior, and they affect the environment through behavior. Let's investigate these by starting from a very different problem, which is image segmentation. So since the 1960s, AI researchers have been trying to create computers that recognize Marilyn Monroe in a photo, or recognize faces, or recognize people. And as we all know, in just the past few years, we've created AI methods that have gotten very good at this. It's taken 40 or 50 years for us to figure out how to do this. It is an extremely difficult problem for a machine to take a photograph and tell you who or what is in the photograph. For our purposes today, we're going to not focus on face or people recognition, but just on image segmentation. Given this photo in the top left, take every pixel and add a binary tag to it. 1, it's part of the foreground. 0, it's part of the background. Of course, this one's a little bit easier because the background is a little bit more obvious. Very difficult to do. What features of this image would tell a machine learning algorithm what's foreground and what's background? Edges, right? So edge detection, that was a very popular method in the 60s and 70s. Look for edges. That's the reason I picked this particular picture. The dress that Marilyn is wearing, there are some false positives. You might infer edges where there aren't, and vice versa. Places where a machine learning algorithm might have a hard time detecting an edge where there actually is an edge there. What else helps you here? Color, that's helpful. Marilyn very helpfully is against a perfectly black background. So am I, but some of you are not.
Like alpha masking, like the depth of field.
Depth of field, so you have to, if you're just given a single photograph, you have to infer depth of field. It's part of the image segmentation problem, very, very difficult.
The way she's posed, in addition to the dress, makes her silhouette not remotely human looking.
Okay.
So, like, it's hard when you're looking at pictures to determine if something's a person, if they're sitting in a way that obscures parts of their body.
Absolutely, right? So obviously her clothing is obscuring her pose. It might be very difficult to do. We're assuming a non-situated, non-embodied machine, right? A piece of code that receives a whole bunch of pixels passively from us. And that's all it has. And it has to use that information to infer where Marilyn is and where she isn't. Let's turn this around and imagine a device that is both situated and embodied and is able to push against the world or interact with the world and use that to infer information about objects out there in the world. We're going to look at a particular example of this. This was a BabyBot that was built in Italy and related to the COG robot at MIT, which we'll see shortly. So BabyBot was designed to do exactly the same thing, to recognize objects in its field of view and infer where the object is and what the object is. But instead of passively waiting for photographs, this robot is embodied and, as you can see in the cartoon, literally pushes against objects in the environment and observe how the world pushes back. Okay, so let's talk a little bit about BabyBot. BabyBot has one arm and it has two cameras, so it has stereo vision. You could take the two camera images and overlap them and infer depth. We're not going to do that. We're going to throw away that information. And instead, we are going to give the robot a continuous video feed from both cameras that have been filtered so that there is one image. And in that image, the pixels are either 1 or 0. In this cartoon here, 0 is represented by the grayed out area and 1 by BabyBot's hand. 1 represents that there was motion detected at this pixel during the last 10th of a second, and a 0 represents no motion during the last 10th of a second. So although you can see what's in this image, BabyBot can't. All it sees at this point is that there is a blob shaped like this, and that blob is in motion. Everything else in its field of view is not moving. That's what BabyBot sees. BabyBot can act on the world by sending commands to the motors in its arm, and it knows when its arm is moving or not. That is what BabyBot has available to it. BabyBot has no other information. So with no other information, what's the best thing to do? The best thing to do is just to start moving randomly. So BabyBot starts sending random actions to its arm, and it's seeing no motion, no motion, no motion, no motion, and then suddenly a blob appears in its right field of view. It keeps sending commands to its arm, and this blob grows and shrinks in its right field of view. It stops sending commands to its arm, and suddenly this blob disappears. BabyBot starts moving its arm again, the blob appears, it stops moving, the blob disappears. What can BabyBot infer from that feedback loop?
If I move the motor, I will saw something.
I will see something. So if I move the motors, I'll see something, and BabyBot decides to call that something me. That's me. That's the definition of self. Definition of self is I send commands, and when the commands are causing motion, I see a blob, and when I don't, I don't. So that thing is me. BabyBot continues sending random commands and is watching this blob, and then suddenly something surprising happens, which is for the exact same command, suddenly the shape of the blob changes. There's this round addition to the blob at the end of the fingertip. That's surprising from BabyBot's point of view. All it knows up till this point is there is a blob of a certain shape, and that shape doesn't really change. Its position changes, but now its shape has changed. What can BabyBot infer from that surprising change in its interaction with its environment?
If previously that's me, and now it's it.
It, okay, right. So if I see this round thing and I stop moving, me disappears, right? The arm-shaped blob disappears. But if BabyBot hit the apple hard enough and the apple rolls a little bit, that round blob may continue to exist even though I am no longer moving. So I'm going to call that thing it, or maybe everything else, right? So just based on the interaction, there's a simple sort of if-then-else statement forming in BabyBot's mind. Things that are me are things that I see when I move and don't see when I don't move. And everything else doesn't respect that correlation. So far, so good? Okay. You can maybe start to see how this game works. BabyBot says, I learned about this thing called me, and by moving randomly, something else happened, and I called that thing it. So let's keep moving and see if other surprising things happen.
Just wondering how it was set up. Was that if statement already a template there, or is BabyBot actually creating that bit of code?
So I'm obviously oversimplifying this experiment. There's not really an if-then-else statement, but it is surprised, right? There is suddenly it discovered a correlation between movement and observed movement, learns that that correlation is respected, and then suddenly that correlation is broken. There's some other relationship. So the definition of it is not it's round and it's an apple. The definition of it is I need to move, then it needs to appear, and then I stop moving, and it continues to appear for a while, and then disappears again, which is the apple stopping its roll. It's learning these things with a machine learning algorithm, but we're going to use the if then else statement as sort of a simplification. So BabyBot keeps moving, and its hand sometimes bumps into another piece of fruit, and other stuff happens. What else might BabyBot start to learn about the fruit in front of it from changes in this push and observe the repercussion loop?
The role becomes different as it goes over other objects.
The role is different, right? This thing called it keeps moving after I've stopped pushing it for a short period of time. But there are other its that roll or don't roll. They appear for shorter or longer times after I touch them and I stop moving. So it is no longer a good enough word because there seem to be other things in the world that act differently. So it replaces the word it with what? Them. Okay, perfect. Them. There are other things. Not everything respects this sensor-motor relationship in the same way. So it's going to come up with this idea of them, and it might start to realize something about relationships across the them, across the things, which is some things keep moving for longer than others, and it detects yet another correlation, which is the shape of the blob of them actually predicts which ones will move and for how long. So things that have this shape keep moving for a long time after I stop moving, but things of this shape don't. They disappear quickly after I stop moving. So I need a word for this relationship between the outline of the blob and how long it keeps moving after cessation of motion. What would be a good word? Mobility, yeah.
Maybe sphereness.
Sphereness, yeah. Mobility, sphereness, rollability. BabyBot keeps moving, and we put, there's an orange there. It comes into contact with an orange. The instant that it touches the orange, the roundness appears. And now that roundness projects an affordance onto BabyBot. There's an advertisement immediately, right? Given the shape, BabyBot can now predict, I can roll it. It's rollable, right? So we introduce adverbs into BabyBot's universe, and now it realizes that by moving around, suddenly things appear and they start to advertise rollability. Perhaps BabyBot comes into contact with the grape and BabyBot is moving quickly. It's going to learn another adverb, not rollability, but what other potential things might happen if it comes into contact with the grapes? Squishability, absolutely. So these two things, the apple and the orange, they maintain their shape. They displace, they move, but they keep the same shape. There's something else like the banana and the grapes that don't keep their shape. Softness, exactly, right? Squishability, softness. So we're going from the adverb, from the affordance to an adjective, right? It's soft. I'm going to start to assign attributes to the things that I encounter in the world, right? Luckily, BabyBot is not literally pushing against people yet, but you get the idea here. We're thinking very carefully about what BabyBot can do, and BabyBot is learning about its world, learning about what it's seeing. It's watching itself move. It's watching the sensory repercussions of its action, or it's receiving visual repercussions to its actions, and building up an understanding of the world from there. We are not presupposing roundness or edges or other visual features. We are letting BabyBot discover them on its own. Question?
What if it pushes against an object that's very heavy?
What if it pushes against an object that's very heavy?
It doesn't respond.
Absolutely, right? So now my own motion is resisted, right? So I'm sending commands to my arm, and maybe my arm flickers in and out of existence because my arm is now no longer moving, even though I'm trying to move it. I can't even see the other object because the other object doesn't move. It's an invisible object from BabyBot's point of view, but maybe it knows there's something special happening at this three-dimensional position. Whenever I reach this position, my arm blinks out of existence, and I'm going to call this position, I don't even know if there's an object there, I'm going to call it heavy, right? Or resistive or something else. If you think about even this simple cartoon, there are hundreds if not thousands of things about the real world that BabyBot could possibly learn by interacting with its environment. If BabyBot sits there passively, like a lot of passive machine learning algorithms do, and again, if we're filtering by motion, there's literally nothing that BabyBot can learn because it can't see anything.
How does it decide like what to do next?
Ah, good question. How does it decide what to do next? Up till now, we've assumed that BabyBot is moving randomly. But one of the keys to learning about the world around you is, after a while, no longer moving randomly, but choosing carefully what to do. We discussed this a little bit when we talked about the evil starfish a few weeks back, where we pulled off one of the legs and it decided what to do next. From what I've told you about BabyBot so far, what would be a good thing to do after BabyBot has learned something about the world around it? When would it switch from doing something randomly to doing something non-randomly?
It can create a mental model and see if I move my arm, what will happen.
If I move my arm, I suddenly see a round blob, and my machine learning algorithm predicts exactly what's going to happen. I'm not surprised. My mental model is matching everything that happens. I'm getting bored, right? I can't generate any more surprise from my environment. So I'm going to start moving non-randomly. I'm now going to start moving at twice the speed I moved before and see if that generates something surprising that I've never seen before. Right? Okay, again, not a class in robotics, so we're just focusing here on how useful exploiting these aspects of a complete agent are and how it could simplify the recognition of objects compared to just subsisting on a hunger diet of pixels. I want to go out in the world and get the information I need rather than waiting for someone to supply them to me. Okay. So again, this idea of complete agents kind of changes not only the way we think about robotics, but in psychology is also changing the way a lot of people think about cognition. We talk about the very word cognition. We usually think of it as something that's inside the brain, right? We get some sensory repercussion, we think about it, and we act. But as complete agents, we are usually interacting with the world and interacting with other agents, other people, or possibly other machines and other robots, so that when we act, there's a sensory repercussion on the other agent. It thinks about what just happened and acts based on that. Its actions become our inputs. We cogitate on that, and around we go. However, if you think about cognition as sort of a cloud or a bubble that we can expand, it covers the other agent as well, because I am forming agent 1 is forming a mental model of agent 2. If I do this, not push against the orange, but ask a question of my human operator, I predict my human operator will do this in response, and I will see whether my prediction of what my human operator did was correct or not. If it's different from what I predicted, I learn something. If not, around and around we go. So it's often useful for situated and embodied machines not to think about just the cogitation going on inside the head of the human or the robot, but something that's expanding to include this interaction and other situated and embodied agents. Okay. So back to affordances, we just talked about this. So hopefully the designer of the door handle is also thinking about the people that are going to interact with the door. As HCI designers, we are trying to create mental models of who or what is going to use the technology, what in the case of our Mars construction team here. And make sure if we think we know what the user knows, we design our technology carefully so that it projects the correct affordances. Okay. A complete agent does not necessarily need to be a physical agent. I mentioned that obviously the rules of gravity apply to an embodied agent because it has a body in the world. in a lot of sophisticated computer games or virtual reality environments, the avatar, the representation of the human user in the virtual world, the avatar has a body, and assuming that the virtual world has some physics and the avatar also has some physics, then the avatar is unavoidably subject to the laws of physics that operate in the virtual world. So again, you may not end up as HCI designers working on robotics. You may end up working for a computer games company or a virtual reality company. But obviously the human user is observing their avatar. They're building up a mental model of that avatar. They are putting themselves in the shoes of that avatar and thinking, what would happen if me, the avatar, pushes against the virtual environment? What do I predict how do I predict the virtual environment will push back? That's what someone is doing when they're playing a computer game or operating in a virtual environment. So how do we design affordances for virtual environments to advertise how the avatars may be able to interact with those environments? What are some examples of affordances that are common in virtual environments?
Something blinking or glowing in the world.
Something blinking or glowing says, I'm interactable, right? It's projecting a particular affordance. Of course, we can just build analogs of physical objects like tables and chairs and conference rooms and houses and so on, which borrow all the affordances that those physical objects project in the real world. Or we can go above and beyond that and add additional affordances that don't exist in the physical world, like blinking and flashing and so on. Okay, so again, just an example with chairs. Here we are borrowing affordances from the real world. Okay, kind of straightforward. Okay, so let's finish today by thinking about this idea of situatedness and embodiedness. We can think about technologies that are embodied but not situated but not embodied, neither or both. Let's start with non-embodied and non-situated technologies. What are some example technologies that would fall into this category?
Maybe the image processing software.
Image processing software, right? Software itself, if we're going to define software as a class, is non-situated and non-embodied.
Wouldn't like any computer that doesn't have like input output of any kind be non-situated, non-embodied?
Exactly, right? So old computers that didn't have a webcam or an accelerometer in them, any computer that's not detecting information in real time is non-situated. And assuming that the computer cannot move itself, it's non-embodied. Situated but non-embodied, we already talked about this one.
Well, I just wanted to go back to the computer thing. Wouldn't either keyboard input or mouse always be kind of real-time input? So how would that be not situated?
It's input, but it's not really input in real time. It's waiting for something to happen. It's event-based, right? So it's, again, maybe it's a continuum, but it's very different from an intelligent light sensor, which is detecting light levels in real time, right? A keyboard will capture keys and put it in the buffer for the computer. So the computer is non-situated. Maybe the buffer that's capturing key presses in real time, that's situated. Situated but non-embodied.
Any device that records temperature.
Any device that records temperature, unless it's a robot that's recording temperature, because that's embodied, right? But any embedded sensor, embedded devices, that falls into that category. We just talked about situated and embodied. Right? So most robots that are recording sensors in real time. We are situated and embodied. Every organism on the planet is situated and embodied. This one's a little trickier. Embodied but not situated. Are there examples of technology you can think of that are embodied but not situated?
Maybe a car.
A car? So a car can act but doesn't necessarily register the sensory repercussions of its action. That's no longer true for most modern cars. But before we started instrumenting cars, they were embodied. But again, if we set aside autonomous cars for a moment, they're embodied, but it's really us that's doing the driving, right? So in embodied technologies, these are technologies that can choose to move themselves. They're embodied, but they do not sense the repercussions of their actions. Sounds like a recipe for disaster, right?
Yeah.
Most of the time, except there is a certain class of technology for which this makes perfect sense. Any ideas?
The Voyager, we sent to the edge of the.
Oh, Voyager. Well, again, we kind of sent it out there, right? It doesn't have much ownership over its own actions. Wind turbines? Yeah, maybe. The strand beasts. Yeah, if you go Google strand beasts with 2 E's, not EA, that is a good example of an embodied but non-situated device. It's a much more common technology than strand beasts. So the IBM plant over in Essex, if you go in the fabrication facilities over there, there are very, very few people, but there are many, many industrial robots. Industrial robots that operate in a factory, a controlled environment. As long as no one gets anywhere near them, they are free to perform or choose to perform certain actions over and over again very, very quickly, because they don't have to worry about edge cases and exceptions. And in some cases, if it's a very controlled environment, they don't even need to sense the repercussions of their actions. They can weld the car door with a good level of confidence that the conveyor belt is going to move the car, and the next time they perform their action, there's going to be a car door exactly there. So just to finish up for today, we looked at these different classes of technology, situated and embodied. You have a quiz due tonight. You're working on deliverable 10. For those that came late, I will not be here next week. However, you will have 2 guest lecturers. Deliverable 10 is due on Monday night as usual. Interim video 1 is due the following Monday night, and all the details about how to perform interim video 1 are now linked from the schedule. So I will see you in a week and a half.